Hello, everyone. Welcome to the LA Data Science Meetup. My name is Szilard. I'm the Meetup organizer and your host today. And I'm really excited about this one. We'll have Hyun-Soo, who is now the main maintainer of the xgboost project. So really the most authentic source on xgboost. Welcome, Hyun-Soo. We also have Eduardo as a Q&A moderator. Many of you know him. We used to run this meetup together when he was in LA. Welcome back, Eduardo. And I'm also excited to be a speaker today. I will talk about GBM benchmarks, comparing various GBM implementations. So let's get started. And maybe we'll know who is the winner. For those of you who don't know me, 25 years ago, I was doing physics and then finance. And 15 years ago, I moved to California to do data science. I also co-founded several meetups and DataScience.LA. I did some part-time teaching, and I'm now here to talk about machine learning benchmarks. Quick disclaimer and deep learning. A lot of people are talking nowadays about deep learning, and especially the media. Deep learning is portrayed as the best machine learning algorithm ever. Also, people say that it almost has magical powers. And indeed, deep learning is great for image recognition and in a few other domains. But I was wondering, how good is deep learning in business prediction problems? So a few years ago, I tried to beat with deep learning this more traditional machine learning algorithms on structured tabular data that's typically found in business applications. And I even enlisted deep learning expert, and we couldn't really beat random forest and GBMs with deep learning. So my version of the previous slide is something like this. So I think if you have a business prediction problem, then deep learning is not necessarily the best. And a bit later, Tnt Chan gave a talk at this LA meetup. He's the original author of xgboost and also the author of MXNet, a deep learning library. So he knows both sides, and he was talking at this meetup about that he looked at Kaggles the previous year, and about 2/3 of them were one with gradient boosting and only about 1/3 of them with deep learning. It kind of split whether the data was structured tabular or image, speech, and those kind of things where deep learning is good at. But there are references from way earlier. These are two great papers from 2006. I think they are still not outdated, so please have a look at these. These two papers took a lot of algorithms and they checked on a lot of data sets, which are the highest performance, and random forest gradient boosting was just as good as neural nets. And I've been using actually random forest and GBMs starting from 2006. I didn't know at that time about these two papers, but I tried out on several projects, many algorithms, and these two seem to be the best. So gradient boosting. Gradient boosting is based on decision trees. In boosting, we are building decision trees iteratively, one after another, and each tree is trying to correct the error that the other trees or the average of the other trees are making. And we do the same in gradient boosting. Let's say we want to use gradient boosting. What kind of open source packages are out there that one can use? I was wondering about this in 2015, and I started this simple limited benchmark, which is available at this GitHub repo. And the gist of it is I was looking at runtime, accuracy, and memory usage of the implementation that were available at the time. And the gist of it is that the best two were xgboost and H2O. This was 2015. And then a few years later, GBM came and it joined the rank of this best GBM implementations. And all these three are available now in R and Python, so really easy to install and use them for either R or Python. What about Spark? Turns out Spark is total garbage for gradient boosting. It's really like 100 times lower and 100 times more memory usage. If you want the details, you can read it on this GitHub repo. I have detailed results, but the gist of it is just avoid Spark for gradient boosting. But people always say, hey, I have big data to use Spark. I cannot use Python. No, you probably don't. Most people don't have big data in most projects. Or even if you have big data, it's only your raw data that it's really big. So once you refine, you combine, you aggregate it, you prepare it for machine learning, your data matrix that's used for learning is not going to be that big. It's going to fit on the memory of one server or even very often on your laptop. So what I think you need is just more memory. It's easy to buy a few hundred gigs of memory or get it on the cloud. Even in 2015, you could get in the cloud 250 gigs of RAM. Now you can get terabytes. And this is a recent survey. I was asking people how much RAM they are using, and most people, they are not using even close to what is available on one single server. And people have figured out that actually they don't need machine learning on bigger data. What they want is faster machine learning, and I fully agree. We want fast machine learning because we run a lot of models. We might run cross-validation, we do hyperparameter tuning, we might do ensemble. So we might run actually thousands of models. And if that takes time, we will need to wait a long time, or we will need to parallelize it on a lot of servers, and that comes to much more implementations. So in 2017, I took my benchmark and I revamped it in a like more lean GitHub repo. And this one, I made it more reproducible and also more easy for me to update the results. So you can just use Docker. It's very easy to reproduce my results. And I looked only at the top gradient boosting implementation. I didn't want to waste my time with implementations that one is using. This is our result from 2018. Here's another survey in 2019. By now, people have figured out which are the best implementations. So most people are using those. And here's something even more recent from a few weeks ago. So you can see xgboost, lightgbm, H2O. And also I added catboost. People started to use catboost, which is kind of the latest GBM implementation. So the results are here for one data set. So actually, things might be different from different other data sets. I think for the runtimes, looking at the one data set is kind of enough as a first approximation. I wouldn't draw any conclusion about the accuracy from this data set, but you can see that on like larger data sets, typically lightgbm is expected to be the fastest. All these libraries have also GPU implementations, though the GPU implementation can be considered as some kind of different product than the CPU implementations. Is usually different code base. And here you can see that on this larger data sets, the xgboost is the fastest. And then you can also try to compare the CPU and the GPU implementations, but that again depends on data and also on hardware. We'll talk about this a bit later. I also looked at memory usage on like larger data set. You can see here 100 million records, and lightgbm is very efficient, uses only 5 gigabytes of memory. For the GPU implementations, most high-end GPUs have nowadays 16 gigs, and xgboost is using on this 100 million records using only 6 gigabytes of GPU memory, so fits really well on one GPU. Catboost still, for catboost, 16 gigs is not enough on those dataset sizes. But for production, I actually like H2O. H2O has bundled with it a product that makes it very easy to spin up web service that will allow you to score real-time, very fast real-time scoring. So this is actually all you need to do to export a model, spin up this web service, and then make request, HTTP request, or it has a REST API, and then you can get scores. It scores fast. Typical model scoring takes like 2-3 milliseconds. Let's dig a little bit more into performance. And first on the CPU. CPUs nowadays have a lot of cores. All these libraries can take advantage of multi-threading and distributing the work on these cores. So what you would expect is that the more cores, the faster it will be. Here's xgboost on 10 million records, and indeed, at the beginning, when you increase the number of cores, you get faster training. Here it goes from 1, 2, 4, 8, 16 cores. However, once you start using more cores, typically these cores are on 2 or more sockets in a very large server, and then each socket has its memory bank, and then once the process, the thread on one CPU needs to have access to the memory bank, which is more closely connected to the other CPU, it can actually slow down things. So you can see that there is a slowdown from 8 to 16 cores if it's 8 and 8 on the other CPU. And if you increase the number of cores, you get even further slowdown. And for smaller data sets, you get even more dramatic slowdown when you have a lot of threads. For example, xgboost on 1 million records or lightgbm. And hyperthreading also doesn't help. It's actually slowing down things. So this was true up to 2020. So in 2020, there were a lot of improvements in xgboost. So the scaling was made much better. And now, for example, from 1 core to 16, xgboost can show a speed up of 5-6 times. And this used to be, before 2020, it used to be actually only 2.5. So you don't get the linear scaling. You don't get 16 times faster training if you have 16 cores or 16 physical cores. You get 5-6 times faster, but at least now it's way faster than this 2.5. And lightgbm, it's something in between. It kind of depends on the data set size. So now also this NUMA slowdown has improved. So you can see xgboost on 1 million records here. It doesn't show that slowdown that before, and also there is less of a slowdown on hyper-threaded cores. But still slow down for lightgbm, where they didn't perform these optimizations. So this problem has been known for quite a while. And I've been advising people to split their model training either by folds or train different models on the different CPUs if they have multiple sockets and don't use hyperthreading. So run one fold on one CPU, another fold on another CPU, and or run different models on the different CPUs, and you can get a lot of speed up versus just running the models or the folds sequentially on all the CPUs. And the difference now with these improvements, it's a little bit less, but I think it's still advised to do those when you're training models. I also have some results on like newer, more high-end CPUs. For example, on AWS, this is the biggest CPU, C9 Metal. Again, I'm running here, I'm eliminating the hyperthreaded, and I'm also running only on one CPU out of the two. This has sockets. So the results are kind of the same. So lightgbm appears to be the fastest on like larger data sets. And also on AMD processors. But actually, most people don't use a lot of cores, so they will not run into these problems. But if you use a lot of cores, you use it because you want faster training, especially over 32, over 64 cores, you need to know about these slowdowns and mitigate the way I was explaining before. What if we want to run a lot of models, like thousands of models on one resource, one server? And actually, the best way to do it is to run one model per core. So to have, you need to have some kind of scheduler that will schedule running, let's say you have 32 cores, and then thousands of models, then you need a scheduler that will feed 32 models on one on each core, and then when a model is finished, then it will feed another model. But for this, you would need to have enough RAM to, you are doing different folds to have all this data in the RAM in the same time. Even if you run in on the same data, if you have different processes, then you need several copies of this data to fit in RAM. What about GPUs? So using xgboost, lightgbm on the GPU is a little bit more involved. You need a GPU, you need the NVIDIA drivers. To reproduce my results, you also need NVIDIA Docker utility. But otherwise, it's not a big deal. Once you're set up, you can just run my benchmark just the same way you run it on the CPU. I also have here some installation notes, how you install the NVIDIA drivers and the NVIDIA Docker utility. And you would also need to install xgboost, lightgbm, and all the other libraries with CUDA support, with GPU support. So this is how you do it. You can look at the details in this Docker file, which is in the repo. And these are just the results that I showed previously. So I have to say that this is on one data set. So the result really depend on the data set. So what I suggest is try several of these libraries on your data set, on your problem, and then see which is faster. But I would expect that lightgbm, maybe xgboost is the fastest, and on CPU and on GPU, xgboost. How many people are using GPUs? This was very little, at least for machine learning with GBMs in 2018. a few more people in 2019, and then I don't really believe 40% in 2020. So I redid this on LinkedIn. The first 3 were on Twitter. So on LinkedIn you get something like 20%, and these are also small samples and with all the biases. So my estimate would be probably 20-30% of people are using now GPUs for training GBMs. Let's look at the memory usage. So GPUs have more limited memory compared to CPUs or general memory, typically 16 gigabytes on higher end GPUs. You can see that even with 100 millirecords, this data fits on one GPU, so you don't even need multiple GPUs. Training time is pretty fast. xgboost runs on 100 million records, 100 trees, it runs in 80 seconds. A bit about GPU utilization patterns, that's very interesting. xgboost uses like 80+% of GPU, as you would expect, and it also interesting to see that it's using only one core on the CPU. This is doing some kind of coordination work. On the other hand, lightgbm uses only about 10% of the GPU. So actually you could run several models training on in lightgbm on the same GPU. However, it uses like 100% of all the cores on the CPU. So lightgbm is a little bit different. It has an OpenCL implementation, and some more things might happen on the CPU, and I'm not exactly sure what's parallelized on the CPU and what's on the GPU. So catboost, on the other hand, also 80+% of GPU utilization. What's different from the previous ones is that catboost allocates all the GPU memory even for one run, so you can't really share the GPU for several model runs. And I think if you want to choose now which GPU implementation, probably xgboost is the most mature. It's also maintained by people who have joined NVIDIA. NVIDIA make sure that they have enough time to maintain the project. And on the other hand, for lightgbm, the GPU implementation was written in 2017, and it hasn't been really touched since then. And it's OpenCL, so it's a little bit different. And now there is an effort to write CUDA implementation for lightgbm, so that might change things. So who is the winner out of all this implementation and CPU, GPU? I think the only honest answer is it depends. It really depends on your project, on your data. So I really encourage you to look at this benchmark more like a starting point, but actually try out all these implementations and see which is the best for your project, which is the fastest training on your data, or if you have some other priorities. And ultimately, all benchmarks are wrong, but I hope mine is useful a little bit. And here is also some kind of summary table of other features of these implementations. So I think the gist would be that in general, but again, it depends on your data, on your project. But if you want fast training and you don't have a GPU, probably like GBM. If you have a GPU, xgboost. If you really care about fast real-time scoring that's easy to productionize, then H2O. But I didn't talk about so far about what's the cost. So there are different comparisons on the internet where people are comparing these libraries based on cost and not on training speed. So here's a quick comparison on one data set, again, one size only. So it turns out that it's not really high-end GPU versus high-end CPU. So the most cost-effective is actually, if you have time to wait for your training to finish, is use like a lower-end CPU system, like 4 cores or even 1 core. That will give you the cheapest. But again, it depends. So I used here demand price. There is also, you can look at spot price. There is all this argument about buy versus rent. So it really depends, and it really depends on your data and size. It's also interesting to see that in the past few months, I have seen a few blog posts from NVIDIA showing that xgboost on GPU is more cost effective than xgboost on CPU. And then I also seen a blog post from Intel showing that xgboost on CPU is more cost effective than xgboost GPU. So I think it really depends on the data size and many other things. But what I think is true is that if you have a business prediction problem with typically structured tabular data, then deep learning is not going to be the best. So random forest and most often gradient boosting will be the best, will be give you the best prediction accuracy. Here are a few more repos. If you have time to look into this, you want to look into this more in depth. And then here you can contact me on any of this. We'll go now into Q&A. So you can ask your questions in the Q&A session, but also you can contact me after the meetup on any of those venues. So thank you for now, and let's go to the Q&A.